Okay, good evening, and I'm by names of Isaac Opio, and I will be very glad to present to you the sample of my project. So this project is about prediction of energy and nutrient composition in poultry feed formulation using deep learning, and we are trying to come up with a multi-output regression approach for feed formulation. What optimization? Optimization is just to achieve the best out of the feed. So starting off with the introduction, poultry feed formulation plays a crucial role in ensuring optimal what? Poultry growth, health-wise, and also based on productivity. And the challenge actually lies in accurately predicting the nutrient composition. For example, metabolizable energy, crude protein, lysine, methionine, calcium, and pH avail based on the complex what ingredient interaction. So traditional methods like linear regression fail actually to capture non-linear what relationships, because here we are trying to come up with formulations that are complex. We are mixing over seven ingredients together. So looking at the back here on the literature review, oh sorry for that. In the literature review, we looked at a variety of literature that was read, and basing on what we have found out, or what I found out, is that traditional methods actually can't analyze what intricate interactions. For example, look at Hamza and Hamza et al. For them, the limitations they found out is that the traditional methods actually couldn't analyze those intricate what interactions between the components. Then also you find that most of the techniques in software were actually not fully adopted in the what in the practical teaching. But then moving forward to the problem statement, we see that feed formulation requires actually balancing multiple ingredients to meet nutritional what needs. So what is the problem? You find that traditional methods do not actually account for what non-linear interactions between ingredients, leading to suboptimal formulation. So the objective here is to develop a deep learning model to be able to predict multiple nutrient values simultaneously in order to improve what the accuracy of the feed formulation. So what is the computational problem? Now, predicting this composition using deep learning based what? Multi-output regression models. That is now the problem. But now the challenge is when you look at the non-linear what? Interactions, the relationships are very complex between those ingredients. When looking at the aspect of multi-output regression, simultaneous prediction of multiple nutrients with interdependencies is really what something challenging. So when it comes to data visualization, we're looking at intuitive representation of complex feed nutrient relationships. And now what is the impact? The impact is to come up with an improved feed formulation, enhancing sustainability and poultry performance while advancing precision what agriculture. So the proposed solution here is we're going to come up with a deep learning based multi-output regression. Shall look at leveraging the ReLU activation and Adam optimizer to model nonlinear what ingredient interactions, and we shall also have heat maps and contour what plots. These ones that will show nutrient ingredients to feed formulations. Basically, that's part of the proposed what solution. Now, the contribution to the computer graphics in feed formulation here include what real time visualization, and also there will be an interactive framework for exploring nonlinear what relationships between feeds, ingredients, and nutrient what outcomes. Then also we shall have a multi-output what regression visualization. Here we shall be visualizing the interdependencies between multiple nutrient what values, for example energy, protein. Then of course we'll look at the aspect of cross-domain what application. Here we shall be extending the physics simulation and engineering graphics to vision what agriculture. That is one of the contributions. Now we'll look at the dataset we have, going through its description. First of all, it consists of what formulations for broiler, starter, broiler finisher, layer chick. These are all the different what different stages, poultry can go through, what different levels in which we can feed our chicken. Then looking at the input features, sorry for that, input features, there are 21 input features, and those are the what proportions of ingredients such as maize, soya bean, fish meal, and very many. Then the target outputs are six. It's what we are targeting: the metabolizable energy, crude protein, lysine, methionine, calcium, and what, and phosphorus. That is part of the what the data set. Now coming to the visualization of our model, we're coming to the methodology. We're looking at it in some 4 5 what basic what aspects. When we look at data collection, here we shall be collecting historical data on feed formulations and what nutrient outcomes. Then when it comes to data pre-processing, we shall perform data cleaning, normalization, and feature engineering. Then in the model development, we are employing a multi-layer what perceptron for multi-output regression. Then in the training, we come up with the hyper parameter tuning, training, and validation as well. Then in the evaluation, we shall use matrices like R squared, MIE, and RMSE. Coming to visualize the methodology, this is what I've just explained. You find that we shall have input data, look at the data pre-processing where you shall have examples like data cleaning. Then here it comes to, let me zoom in a little bit. Sorry for that. Oh. Let me zoom out. When it comes to model development, you find that we shall have some layer design, activation, what functions. Then we look at the model training. That is basically the same what we're just visualizing what I've just explained back there. Coming to the architecture is something really, really very simple that can be broken down into four aspects. We'll have the input layer that has got the 21 input what features. These are the ingredients that we are what trying to mix together and formulate. Then the hidden layers for the processing, where it has about 32 to 256 neurons each, and a really what activation function. This is just in the computational bit of the model. Then look at the output layer. It has got six outputs. Those are our target what? Our target outputs, the target variables. We want to be able to see, okay, what is the impact of this formulation on ME? This is that ME here stands for metabolizable what? Energy. What is the impact of this formulation on the crude protein? What is the impact of this formulation on lysine? Then training shall employ, of course, the Adam optimizer as usual, the mean squared error loss what? Function. Exploratory data analysis. When you look at the results, you find that the dataset consists of 22 input features, which has maize, soya bean, and whatever. Then in the analysis, we used histograms to visualize and reveal that most of the features, such as maize and soya bean, follow a right skewed what distribution. Now, a right skewed distribution, saying a right skewed distribution shows that actually most values fall within what a certain given range, and a few of them are what exceptionally what high. Then when you look at the correlation insights, the correlation matrix, as will be shown below, highlighted a strong positive correlation between some of the ingredients. For example, when look at the correlation between the metabolizable energy and crude protein, it was really, really high. So this one was suggesting that the relationship could actually be leveraged in what predictive modeling. When the correlation is really, really high, you find that a change in one could really, really affect the other. So as you can see from these graphs, you can see that some are right skewed, this one is a little bit left skewed, where we have metabolizable energy and all that. So that's all the histograms. And look at the correlation matrix here. Let me zoom this. It really shows you that the correlation relationship between most of those ingredients alongside what other ingredients that were used as what the input variables. So coming to the results, the model was trained over what 100 epochs, and we achieved some mean squared what error, a very low one. The mean squared error was a little bit low, but looking at a table that related to the actual values versus the predicted values, for example, the one shown here, this is what we revealed, that the metabolizable energy, the actual value was 3,000, but the predicted one from the model was 3,550. Looking at crude protein, the actual one was 22.1. But coming to the predicted value, you have 26.3. Lysine was 1.3. Then the predicted one was 2.37. So This calls for a little bit of adjustment of the what of the model, fine tuning, to better the results of the model. And in the visualization here of the training, we're looking at this graph that elaborates the training and validation loss over some FOX. Find that as we're increasing the FOX, the the training and validation loss actually was dropping down. No, there was a trend whereby it suddenly dropped and then tried to what? To gradually decrease. Then in the scatter plot that we were visualizing actual versus predicted nutrient values, you realize that yes, the values are trying to conform to the same region. So this one actually shows that wow, the model is actually trying to what? To produce output that is required. So when you look at the values, the actual ones versus the predicted ones, they are all within the same what? Region in the scatter what? The scatter plot graph. Next slide. Next slide. So looking at computer graphics in the feed formulation analysis, we used histograms for distribution analysis where we visualize the numerical features, for example, metabolizable energy, crude protein. But here are the key insights. The skewness, the positive skew was actually many. It was there. There was a positive skew in many of the features. Then the metabolizable energy clustered between 2,800 to 3,200 kilocalories per kilogram. Then looking at the outliers, we detected that lysine and methionine content. We detected outliers in lysine and methionine content, and this one requires actually what? Now further investigation. And what is the impact of this? It will imply what? Exploration of large data sets to aid anomaly detection and decision making. Then the correlation matrix, of course, for the feature relationships, it was actually to visualize the relationship between ingredients and the nutrient what outcomes. And what were the key insights here? We saw there was a strong correlation between crude protein and metabolizable energy. So adjusting any of these could really affect the other because of the strong what relationship. Then in the weak correlations, we managed to look at calcium and phosphorus actually acting independently of energy and protein. So the impact, what is the impact? This actually enhances real-time decision making through intuitive and multivariate what? Visualizations. So that is my presentation about the model, and I hope to produce better of the model. Thank you so much.